In this video, I'm going to show you a tutorial on how to use NetworkX as a Python package to do your network analysis and do a bit of visualization at the same time. And as I said in the other video, it's very important to study the different networks, for example, social networks where people act as nodes, and the network determine how connected the two profiles are by various parameters. And this helps, for example, recommending the jobs, connections, political agendas, all these sort of things. For example, think about a political party where people within the party are having dispute among themselves, and if the party splits into two different groups, uh, probably you want to be able to identify which members would join which party, and then social network analysis is a very good tool to get an understanding on such a thing. For example, another application is where you want to minimize the spreading of rumors. Then it's also important to have an understanding of the social network that you're dealing with. So in this tutorial, we're going to learn a bit about a tool that can help you on doing the network analysis, which is called NetworkX. And what I'm going to show you at the beginning is a bit of basic concepts about node and edge attributes and bipartite graphs. And then after that, you're going to have a look at a bit of more complex data set and do a bit of network analysis, not necessarily the data visualization, but for understanding the concepts and the network and the connections in the network. And at the end, I'm going to show you a few cool network visualization taken from the NetworkX own repository, just to show you that it is a versatile visualization tool as well, but we are not really focusing on that visualization aspect of the NetworkX in this video. But if you are interested, you can have a look on the NetworkX manuals and tutorials. I will put a link in the description box to that as well. You can also get the link to this code and any dataset that is used here in the description box. So let's start. What we need to do first is basically to import the packages that we need. And for today, basically the most important thing that I need is the NetworkX, that I'm importing it as NX, and you need to have it installed on your computer, which is quite easily. And then I'm going to build a simple graph, edges connecting different nodes. As we already said before, it could have some attributes. In this case, we are thinking about the weights that determines the strength of relationship between two nodes. And just to have a bit of more flavor, we're also going to add some different relationships. For example, if two people, we are thinking about people in this concept, in this context, are family members, are friends, or they are enemies. So what I'm going to do here is first build an empty graph with the network X, and then I'm going to add edges basically. And at the same time, when you're adding edges, you're adding nodes as well. So basically what I'm saying in the first line is that I want to add an edge between two people called A and B, and the relationship, the strength of the relationship, think about it, is like 13, and in this example it's probably one of the strongest one, and they are friends. Similar to that, B is also a family member of C and the weight is 9. B is also a friend of D. The weight is 7, which is a bit lower than the previous ones. And E and B also are friends. E and A doesn't have that much of a good relationship with each other. And B and F are family members. And this is what I'm going to have here, and I'm going to build my graph. And this is basically give you an overview of the edge. It's basically what you put there: the weight, the relationship, and the nodes. You could also assign some roles to the nodes. What I'm doing here, for example, I'm saying the A is a trader, B is an analyst, and C is a manager. We could also, let's copy this, and see if we could see how this looks. Yeah, so this is basically how our graph looks, and as you see, B has the most number of connections. This is obvious from here because we more or less connected B with everyone. So yeah, it's all really B with E, F, D, and C, and as you see, A is also connected to B, but also to E. Everybody else is also only connected to B. So as you see, even within this simple network, you can immediately get a feeling of the connections. Nobody is connected to each other except B, that the holding network together, and A, that has another relationship with E. And if you look at the labels, this is not actually a very close relationship. They are enemies. So it gives you an indication just by looking at this graph, and if I had put the labels there, you would have seen, you would get a lot of understanding by just looking at this simple graph. We talked about graphs already today. What I didn't mention in the previous video, and I'm going to explain it now, is that it's not always the graphs you're seeing here only with one connected component. And connected component is basically that everybody you could get to them to each part of the graph you want. You could have several different connected components without any relationship. We could also have another form of graph that we are calling it bipartite graph. And let me give you an example to get a better understanding of what a bipartite graph is. For example, suppose we are working in a company where the users earn money or prizes if the team or players selected by them win in a particular match. And we are given the responsibility to find the important players or teams which the users will be targeting. So the networking between the users and the players selected by the team is a bipartite graph. In another word, a bipartite graph is a graph whose node can be split in two different groups, G1 and G2. I'm going to build a bipartite graph, and then we're going to take it from there. So what I'm doing here is, as before, I'm building an empty graph. Then I am dividing my nodes into different categories. So A to E is group 1, and 1 to 4 are group 2. And basically what I'm going to add edges between these two groups. And I'm going then to check to make sure that these are a bipartite graph. And in the sense that there are no edges where there shouldn't be an edge. Let's have a look. First, let's build a graph and check if it is a bipartite graph, and NetworkX tell me that it is. But then let me draw it, and then you can see how it looks. As you see, we have my group 1 here and group 2 here, and there is no edge between the members of the same group. This is a bipartite graph. You don't have any edge here, but the edges are across the group. So you mean from group 1 to group 2. You don't see any edge between the members of group 1, and you don't see any edge for the members of group 2. So this is also a small tutorial on how to build and draw a bipartite graph. It's enough with that. Let's get to a bit more practical discussion, basically doing a bit real analysis. And here what we are going to have, it's a data set that I'm going to put in the GitHub folder, and then you can have a look, and then we are going to have a analysis here, and then you can give it a try. And remember that before beginning the tutorial, you will need to download the two files together that constitutes our network dataset. That one is Quaker's node list and then Quaker's edge list, and then you can have a look at that. And let me give you a bit of context about what the example is. Before we had Facebook Friends, there was a society of friends known as Quakers, and this was founded in England in mid 17th century, so it's an old-fashioned Facebook in a sense. And they were Protestant Christians who dissented from the official Church of England and promoted broad religious toleration. So what we have here is basically the files related to this group, and their numbers grew rapidly through mid and late 17th. And what you have here, basically the name of the members and how they are connected to each other. So let's get to the actual work. I have already saved the file on my local drive, and then I'm going to import the packages that I need. And remember that because we are going to have a look at the community that they built as well, you need to import the community from NetworkX algorithm. It doesn't come only if you import NetworkX. Okay. And then, as I said, I have two different files, two different CSV file, one for nodes and the other one for edges. And I'm going to load them. Let's have a look at how many nodes we have and how many connections we have. So basically we have 119 nodes and 174 edges. As before, I'm going to initialize a graph object with the following command. And then what I'm going to do after I created the object, since there is nothing in it, I'm going to add the list of nodes and the list of the edges. As simple as that. I add nodes from the node names and I add edges from the edges. Then I get some info. Basically, it is a graph. As you saw before, we have 119 number of nodes and then 174 number of edges, and the average degree. If you remember, the average degree was basically a degree of a node is a number of edges adjacent to it, and this is the average of all degrees basically. Okay, so let's get to adding some attributes to it. These are the attributes that I would like to add to my my network, and by adding attributes to both node and edges, you could have more information about all of them. So let's see what we can have. We can have at the attributes that we want to add is the historic significance, the gender, the time of the birth, the time of the death, and then their ID. And then what I'm going to do is basically I'm going to say if the person's historical significance, you're going to put them in a list. Then index 0 is when you start counting in Python, and so the person's historical significance will be index 1, then gender will be index 2, and so on. So we build our dictionaries like this, as you see, historical significance node 1, 2, 3, 4, 5, and so on. And now you have a set of dictionaries that you can use to add attributes to nodes in your graph object, and the set node attributes function takes 3 different variables. the graph to which you're adding the attribute, the dictionary of ID attribute pairs, and the name of the new attribute. And the coding for this, you can find it here. Basically, I'm just writing them more clearly in a sense. Now we have all these 6 attributes, and we could access them anytime we want. For example, if I want to print out the birth years of the nodes, of all the nodes, I'm going to do that by looping through them. So for all the nodes that I have, I'm going to go to the node and find the birth year. And this is what you see. These are all the people that are in this data set and their year of birth. If you remember, we discussed about network density before in the previous video. So this is something that I'm going to try, and it's a good metric to begin your network analysis with. And as I said before, this is simply the ratio of actual edges in the network to all possible edges in the network. You know that you could draw edge between every 2 nodes, but this is not what happens in reality. So what we are doing is basically getting the ratio of what exists and over what could exist. In an undirected network like this one, there could be a single edge between every 2 nodes, but only a few possible edges could be present at the moment. And network density gives you a quick sense of how close-knit your network is. And the good news is that it's quite actually easily done in Python, but with one single line comment. And this is as simple as, where is it? Yes, density and X density for the graph G. And this is what we are getting here. The output of density is a number, so that when you'll see the value when you print your value, and in this case the network is the density of network is approximately 0.002, and on the scale of 0 to 1, this is not actually a very dense network, which is what you could also see when we are doing the network visualization. I can actually try to do that. Let me copy that so I don't need to print it again, type it again. Probably it was easier if I had, yeah, you see it's not that dense, the network. Okay, not turn that thing off. So this is about the network density. So another thing is the shortest path measurement. That is a bit more complex, and it calculates the shortest possible series of nodes and edges that stand between 2 different nodes. Something hard to see in a large network visualization. If you have something really, sorry. If you have something very close to each other, you can't really identify the path, and then it's difficult to identify the shortest path. And basically this measure is essentially finding friends of my friends of friends. If my mother knows someone and I don't know the mom, is the shortest path between me and that friend. And to calculate the shortest path, you need to pass several input variables to your function, which is the whole graph, your source node, what is the node that you are interested in to be connected to somebody else, and the target node, which is that somebody else that you are interested to be connected node. So let's assume we have 2 different people. We know them, Margaret Fell and George Whitehead, and we want to know the shortest path between those 2. So Fell Whitehead path, and this is NX shortest path. I have the graph, the source, and the target, and then I want to see this. As you see, there is only George Fox between these 2. So this is quite a short path. And I can also print the length, which shows it. diameter is the length is 2, as you can see. Another fact that we can another metric that we can derive from the network analysis is the diameter, and this is simply the longest of all short paths. After calculating all short paths between every possible pair of nodes in the network, diameter is simply the length of the path between the nodes that are furthest apart, and this is to give you a sense of the network's overall size, basically the distance from one end of the network to the other end of the network. And we simply use it with an x diameter on the graphs, but we need to keep in mind that it will only answer when we have a connected graph, and the graph we have here is not connected. So let's have a look. If I do only an x diameter, I'm going to get an error because it is not connected. So what I'm going to do, first of all, I'm going to show you that this is not connected. I'm going to check whether my graph is connected, meaning that there is no part of the graph that doesn't have any edge to the other part of the graph. And then, if not, I'm going to calculate all existing connected components, and then I'm going to look at the largest connected component, because as I said, it's going to give you the sense of the size of the graph from one end to the other. So it does make sense if we look at the largest one. And then based on that, we're going to calculate the diameter of the largest connected component. So let's see how this works. As you see, this one gave false, and the network diameter of the largest component is 8. Another thing that we could have a look is that triadic closure. And triadic closure supposes that if two people know the same person, they're likely to know each other. Basically, if Fox knows both Phil and Whitehead as before, then Phil and Whitehead may very well know each other. So completing a triangle in the visualization of 3 edges connecting Fox, Phil, and Whitehead. And the number of these enclosed triangles in the network could be used to find clusters and communities. So let's see, what do we have here? Triad closure I'm going to define is here, and one way is basically to using the clustering coefficient. Because of this clustering tendency, and the structural network measure that we use for that is transitivity, which is the ratio of all triangles over possible triangles. And a possible triangle exists when one person, for example Fox, knows 2 people, Phil and Whitehead. So transitivity, like density express how interconnected the graph is. So let's see, what do we have here? And the triadic value that we have here is 0.1694, and it is somewhat higher than the density that we calculated sometime before. It was 0.02. Okay, so let's get to another important thing that we are interested in, and we already discussed that in the previous video. The centrality measure is one of the important thing, and there are so many ways approaching the question which nodes are the most important ones, and there are many different ways of calculating them. Centrality measure is one of them. Of course, we also have degree, could measure what are the important things, but let's go through them and see how that could be done. Calculating centrality for each node in network X is quite as simple as the network-wide metrics that we have seen already above, and it still involves one-line comments, and all the centrality commands produce dictionaries in which the keys are nodes and the values are centrality measures. That means that they are ready-made to add back into your network as a node attribute, like you did previously when you were adding these attributes to your node. So what we do is basically we start calculating degrees and adding it as an attribute to the network. So we have this, for example. Now we have added a degree here as well, and we check it for William Penn. You see, these are the things that we had before: historical significance, gender, birth year, death year, and ID. And now we also have degree here. And these results are useful for more than just adding attributes to your graph. Because you're in Python, we could also sort and compare them. For example, we could have a function called sorted, and then sort a dictionary by its key or values. For example, the top 20 nodes of importance. Let's have a look here. For example, we have this sorted degree here, and then I'm printing the first top 20. So as you see, George Fox has the highest degree. That's somewhat meaning that it has the highest connection. So let's get to our centrality measures. We have eigenvalue, and we are going to have a look at eigenvector centrality and betweenness centrality here. This one previously was the only centrality based on the number of edges that are going out of the end node, but this is not the only one. So let's see what is betweenness centrality and eigenvector centrality. Eigenvector centrality is a kind of, it's somehow an extension of the degree. It looks at the combination of the node's edges and the edges of the node's neighbors, so it's a bit more complicated. And eigenvector centrality basically cares if you are a hub, but it also cares how many hubs you are connected to you. And it actually makes sense, because it is good to have many number of connections, but it is even better that you have some connections who also have a number of connections, so you have a larger reach. And another one is betweenness centrality, that is a bit different from the other two measures that you saw. It doesn't care about the number of edges any one node, a set of node has. Betweenness centrality looks at all the shortest path that goes through a particular node. And to do this, it must first calculate every possible shortest path in your network. So it's good to know that calculating betweenness centrality may take a longer time than calculating other centrality measures. Betweenness centrality is also expressed on a scale of 0 to 1, and it is good when we want to find the nodes that connecting to otherwise distant parts of the network. So let's see what we can get here for this one. So we have betweenness, and we're going an eigenvector, and we're going to add them actually as the new attributes to our network. We calculate this, and then have a look at the betweenness and sort them. So now William Penn, what was here? So this changed a bit here. When we are looking at the centrality, betweenness centrality, the importance is different. So now William Penn is the first one that we have here. We can also have a look at the communities. Another common thing to ask about a network dataset is what the subgroups or communities are within the larger social structure. Is you have one big happy family where everyone knows everyone, or it's a collection of smaller cohorts that only stick to each other? And the field of community detection network is designed to answer these sort of questions. And then there are many ways of calculating communities: cliques, clusters, many other ways. But One of the more popular methods is modularity. Modularity is a measure of relative density in your network. Basically, a community has high density relative to the other nodes which is within its module, but low density with those who are outside the community. And community detection and partitioning in network X needs a bit more setup than the other metrics that you saw. And you can find the documentation in network X, but there is one way that we're going to try here, and that is greedy modularity communities, which tries to determine the number of communities appropriate for the graph and groups all nodes, and then groups all nodes into subsets on these communities. So let's calculate this first. And then what we do here, we first create a blank dictionary, and we then loop through the list of communities and keeping track of the number for the community, and then we can add modularity information as we saw before as an attribute. And another thing that we can have a look is the eigenvector centrality as a ranking that gives a sense of importance of people within each modularity class. Now we have these modules somehow, and we want to see who is important where. And now we are going to give it a try here. First, we get the list of the nodes in each class, each module basically, and then we create an eigenvector, and then we sort the dictionary and print the first 5 top results. So basically this is what we are getting. Class 0 William Penn is another one that is important, and the eigenvector centrality is actually pretty high here. And in a smaller network like this, a common task is to find and list all modularity classes and their members, and you can do that basically by looping through the communities list. Yeah, we had class 0 there, module 0, however you want to call it. Then we have class 1 here, class 2, class 3, and we see at the end we have 7 of those. Let's see what I have next. I want to show you what I want to show you basically is that whatever you are getting here, you could export it and use it in the other visualization tool. For example, if you want to download your data and play with it in Gephi, which is a visualization tool, which is actually a versatile tool, and it would be good if you have a look at it for your future use, then you simply can write whatever information you have here, and then it will be saved in your working directory. So what you saw up to now was basically how to use Network X to get some sort of different metrics, but I didn't show you really much visualization because this dataset was not suitable for doing that. But to have a bit more fun, I'm going to show some of the examples from Network X. You could also find the files, the codes there, but basically just to show you that we could build beautiful stuff here on Network X as well. And basically what we are doing here is building a random geometric graph, so it is not really meaningful. We are building a random graph, and the position is stored as an attribute to the data. Then what you see, let me draw it and then I can probably explain better. Then you have a center for your graph based on the attributes that you define. And the further you get from you could define it in a way that the further you get from the center, the lighter the color becomes. So color by path length from node near to center. This is what it says here. So this is one of the things that you could do with Network X. You could visualize and color your nodes based on different measures. So you don't need to have the same single color for all nodes or for a set of nodes. It could be a dynamic coloring, which is very important and very useful, and you could use that. Another one, it actually needs GraphViz or PyGraphViz to visualize this. So I have already installed it in my computer. So let's see what that does. And here illustrates the sudden appearance of a giant connected component in a binomial random graphs. So these are all random graphs, and it is only for the purpose of seeing that the visualization, how that could be. And let's see, how does this one look? Yeah. So as you see, this is a different form of visualization. And it shows also the p-values on the graph. It shows different connected components, and then it identifies the largest connected component, which you can find here. And finally, one last example. This is the new Smiles example, which returns an undirected graph over 128 where is this 128 cities from the US, and the attributes connected to each of these nodes is basically their location and the population data, and the edges are labeled with the distance between different two cities. And this is how then they are going to look. This has 128 cities and 8,128 edges. So you are able to visualize pretty large graphs using Network X. And there are so many more examples if you go to its own website, a Network X tutorial gallery, and you could play more there. But I think that's enough for today. You can find the code in the GitHub repository, and I will put a link in the description box below as well. Enjoy playing with Network X and network analysis. See you in the next video and next lecture.